Okay, in today's lecture we're going to cover the section 3.4 material on quadratic functions and applications. So this will be our last bit of the chapter 3 material, which has primarily been a review of some pre-calculus concepts which we'll use throughout the course. And in the first part of this chapter we've been dealing with linear functions or piecewise linear functions and their applications. So now we're going to consider quadratic functions and some applications. So recall that a quadratic function is any function of the form f of x is ax squared plus bx plus c, where a, b, and c are constants, with a being non-zero. So that is some polynomial whose highest term is x squared. Now the graph of any quadratic function we know is a parabola. In particular, if a is positive, that is if the coefficient of x squared is positive, then our parabola opens upward. And if a is less than 0, our parabola opens downward. So let's look at some examples graphically here. The easiest example to consider is the graph of y equals x squared. So we can graph this function. We recognize it as a parabola opening upward. We know it passes through the point 0, 0. So when x is 0, y is 0. When x is equal to positive or negative 1, our corresponding y value would be plus or minus 1 squared, which is positive 1. When x is equal to 2, y is equal to 4. And when x is equal to negative 2, y is also equal to 4. And when x is equal to 3, plus or minus 3, y is equal to 9. So we have 2 points up here, and our curve would be the parabola passing through those points. So a parabola is sort of this bowl-shaped curve opening in the upward direction here, since the coefficient of x squared is a positive 1. Now if we were to change the coefficient, let's say we make this y equals negative x squared, well, we would have the exact same curve, but where all of our positive y values are now made negative. So when x is plus or minus 1, we have y would be negative 1. When x is plus or minus 2, we would have y is plus or minus 4. And when x is plus or minus 3, y would be plus or minus 9. So we would have the parabola opening in this downward direction if the coefficient of x squared is negative. Now we can, or in the examples we've looked at here, we have y is 1x squared or negative 1x squared. In general, our coefficient for x squared is some non-zero constant a. It doesn't just have to be plus or minus 1. So how does that value of a affect the shape of our curve other than the direction that our parabola opens? Well, if the absolute value of a is less than 1, so that is if we have some number between negative 1 and positive 1, then our parabola would open wider than the graph of y equals x squared. Whereas if the absolute value of a is greater than 1, if we have any number greater than positive 1 or less than negative 1, then our parabola will be narrower than the graph of y equals x squared. So to illustrate this, let's look at a couple of examples. Let's say that we take the graph of y equals 2x squared. So when x is equal to 0, y is still 0, so we're still passing through the origin. When x is plus or minus 1, our y value would now be 2. since we've multiplied our x squared function by 2, we get larger y values for each x. Now when x is equal to plus or minus 2, we would have plus or minus 8, or positive 8, rather, for x values of plus minus 2. So we have the following parabola for the graph of 2x squared, and we can see that this is opening a little more steeply, or it's narrower than the graph of our original x squared function. So maybe for comparison's sake, let me use some different colors here. Let's say that y equals 2x squared. I'll plot in red as this curve we've just shown here. Our original function, y equals x squared, let's plot on the same set of axes. So when x was plus minus 1, we had plus minus 1. When x was plus or minus 2, we had 4 for our value. And when x was plus or minus 3, we had 9 as our value. So the graph of x squared is opening a little wider than the graph of that 2x squared. Now let's say that we change that a little bit. Let's say we consider also the graph of y equals 1/2 x squared. So if we make the coefficient of a number less than 1 in magnitude, let's see how that affects our shape of the curve. So here, when x is 0, y is 0, so we're still passing through the origin. When x is equal to 1, we would have a value of 1/2. When x is equal to 2, we would have a y value of 2. When x is equal to 3, we would have 9/2 or 4.5. When x is equal to 4, we would have 4 squared is 16, and then half of that would be 8. So we have a parabola that looks something like this. It opens a little wider than the graph of x squared. And if we were to take, say, like negative 2x squared, well, we would have a parabola then just opening downward. Instead of upward. So if we were to take, say, y is negative 2x squared, or y is negative 1/2 x squared, we would have the same sort of parabolas, but then opening in a downward direction instead of the upward direction. Okay. So we've seen a little bit about how the coefficient a will affect the direction in which our parabola opens, as well as how wide or narrow that parabola is opening. So let's consider what else the graph of a parabola might tell us, and some associated terminology. So in the event that a parabola is opening upward, the lowest point on the graph of that parabola, or on that parabola, is called the vertex. And when a parabola is opening downward, the highest point on that parabola is also called the vertex. So if we're considering, let's say, a parabola that looks something like this rough sketch here, we have a parabola opening in the upward direction, and so this lowest point on the graph of that curve is called the vertex of the parabola. Now, if we have a parabola that's opening downward, let's say it looks something like this, then the vertex would be the highest point on that parabola. So depending which direction this curve opens, we might have a smallest value or a largest value for our function, which corresponds to this point which we refer to as the vertex. Now, some other terminology to go along with this, we would say that the vertical line that passes through the vertex of a parabola is called its axis of symmetry. So for instance, let's say that we have the parabola shown here, opening upward, where our vertex would be this lowest point on the curve. The vertical line, which passes through that vertex, is referred to as the axis of symmetry. And it's referred to as the axis of symmetry because we can see that our curve is symmetric about that axis. So it's if we were to reflect it about the axis or fold it on that axis, we see that the curve matches up with itself. So if we had another parabola, let's say something like this, where our vertex would be the largest value on the curve, well, our axis of symmetry would be the vertical line that passes through that vertex. So regardless of whether it opens upward or downward, the vertical line passing through the vertex of a parabola is that axis of symmetry. Okay. Now, for any quadratic function, we can express the quadratic function in what's called standard form. And the standard form is a function of the following form. F of x is equal to a times x minus h quantity squared plus k. And this theorem says that the graph of such a quadratic function is a parabola whose vertex is given by the point hk. So here, this point hk is the vertex, and the values of h and k can be read off directly from this function. So h is the value that I'm subtracting from x inside the parentheses, and k is this constant value that I'm adding on the end. So those give us the x and y coordinates for the vertex of a parabola. Now, in the event that a is positive, we have an upward opening parabola, and if a is negative, we have a downward opening parabola, as we've already mentioned. So in this next example, we are asked to determine algebraically whether the given parabola opens upward or downward, find its vertex, and then sketch the graph of this parabola. So in part A, we have our function f of x is x plus 4 quantity squared minus 3. And we see that this is already written in the standard form for the equation of a parabola. So we can read off our vertex directly here. Our vertex would be the point hk, where h is the value that I was subtracting from x inside of the parentheses. Now here, if we have x minus 4, or x plus 4 squared minus 3, if I want to think about that as subtraction, I could think about this as x minus a negative 4 squared minus 3. So here the value that I'm subtracting from x is my h, and the constant that I'm adding on the end would be k. So in this example, our vertex would be the point negative 4, negative 3. So let's sketch that. We have the following point as our vertex, and we need to sketch the graph of our parabola. So we could indicate, well, which direction is it opening? This was part of our problem statement, indicate which direction it opens. And in this case, the constant a in front of our x minus h squared term is a constant 1. It's positive. So this is a upward opening parabola. It's going to be centered around some axis of symmetry, which would be the vertical line passing through -4. And so to visualize what our parabola looks like, well, we could choose some values of x about this axis of symmetry and plot the corresponding y values. If our axis of symmetry is at x equals 4, let's see what happens if x were equal to, say, -3. If x is equal to -3, then our y value would be -2. So we have the point -3, -2 on our curve. And if x is -5, that is 1 unit to the left of our axis of symmetry, then our y value would also be -2. Now, if x is equal to, let's say, -2, move 2 units to the right of our axis of symmetry, we would have a y value of 1. And similarly, since this is symmetric about the axis, if we move 2 units to the left of our axis of symmetry, we would have the same y value of 1. So if we choose some other values, let's say x equals -1, we would have 3 squared is 9 minus 3 would give us a value of 6. And if we move 3 units to the left of our axis of symmetry, we'd also have a y value of 6. So we start to visualize our curve in this way. So we have a parabola that looks something like this. Okay. Now in part B, we have the function g of x is -2 x minus 3 quantity squared plus 1. So immediately, we recognize that our constant a is a negative number, so our parabola will be opening downward. And let's see if we can identify its vertex. So here, our vertex is hk, where the value h is the number we're subtracting from x inside our parentheses, in this case, 3. And the k value is the constant that we're adding on the end of our standard form equation, which is 1. So the vertex of our parabola is 3, 1, and the axis of symmetry is the vertical line passing through that vertex. So our parabola is opening downward from here, so to visualize it, let's look at some other points on the graph of this parabola. So let's say that we chose a value of 2. If x is equal to 2, we would have a y value of -1. And so if x is equal to 4, 1 unit to the right of our axis of symmetry, we would have the same y value of -1. Now, if x is equal to 1, we have, let's see, -2 squared would be 4, times -2 would be -8 plus 1, so -7. So if we move 2 units to the right of our axis of symmetry, we would have the same y value. So our parabola is opening downward. It has its vertex at the point 3, 1, and it looks something like this. We see it's a little more narrow than the graph of our parabola in part A, because we were multiplying out in front by a constant -2. Since the absolute value of that constant is 2, our parabola is opening more narrowly than the one in part A. Okay. Now, a problem of interest is determining the vertex of a parabola. And we've seen that if we can rewrite, or if we have the equation for our function in the standard form for the equation of a parabola, we can read off our vertex directly. and then plot some points to graph our parabola. So this form that we were considering for a quadratic function is called the standard form. Again, that is the form f of x is a times x minus h quantity squared plus k. And we can write any quadratic function in that standard form by using a technique known as completing the square. So let's look at some examples of this process of completing the square. So for this next example, we are asked to determine the vertex for the graph of a quadratic function. And to do this, we want to write it in a standard form by completing the square. So let's look at how that works in part A. We have the function f of x is x squared plus 6x plus 5. And so usually what I like to do here is start by grouping the terms x squared and x together. So anything involving the variable x, I'm going to group together. And then any constant term that I have, I'm going to leave outside of this set of parentheses. And the question that I'm asking myself is, what constant would I need to add to this quadratic in parentheses so that it could be factored as x minus h quantity squared? That is, I need it to factor as a perfect square. Now, in general, if you have something of the form x squared plus bx, the term that you want to add on the end of this expression to factor it as a perfect square would be half of the b coefficient. So whatever number appears in front of x, you want to take half of that value and square it. And this allows you to then factor that quadratic as x plus b over 2 quantity squared. You can see that if you were to expand this expression, you get exactly the term that we have here. So in my example in part A, we have x squared plus 6x. So my coefficient of b here is 6. So the term that I want to add on the end is half of that value, which would be 3 squared. Now 3 squared would be a value of 9. So I'm going to add 9 on the end of this expression. And then I had my constant plus 5 on the end. But let's think about what we just did. So I've added a constant 9 to my function. So in order to keep the value of the function the same as what we were given in the problem, well, if I added 9 to the value of the function, I must also subtract 9 from the constant term on the end, so that these plus minus 9 terms will cancel, and I'll have the same f of x that we had in the previous line. So any number that you add here, you must also subtract from the end. Now this allows me to rewrite this function in the following form. X squared plus 6x plus 9 can now be factored as x plus 3 quantity squared. And then on the end, my plus 5 minus 9 reduces to a negative 4. So this now has the standard form for a quadratic function. And from here, I can find my vertex. The vertex of this parabola would be the point negative 3, negative 4. Now, why negative 3 there? Well, I have x plus 3 in parentheses, which I can think of as subtracting a negative 3. So that gives me my negative 3 for the x coordinate. So let's look at another one. In part B, we have g of x is x squared minus 12x plus 33. So using the same approach as in part A, I might think about the x terms as being on their own, x squared minus 12x, and then my plus 33 on the end. And for this expression in parentheses, my coefficient for x, which is the value b, is negative 12. So the constant that I want to add onto the end of that quadratic to factor it as a perfect square would be half of that value, which would be negative 6 squared. So I'm going to have plus 36. And then on the end, I had a constant plus 33. But here, since I've added 36 to the value of this function, on the end, I must also subtract 36. So that these two terms will cancel, and I'll have the same value for g of x that I started with. Now, what this buys me is the following. My x squared minus 12x plus 36 can now be factored as x minus 6 quantity squared. And then on the end, my constant plus 33 minus 36 leaves me with negative 3. So this would be the standard form for that g of x function. And from here, we find that our vertex would be 6, negative 3. All right. So in part H, or part C, we have a function, h of x, given by 2x squared plus 8x plus 6. So let's think about how we can handle this one. So this one's a little bit trickier because here I have a coefficient in front of my x squared term that's something different than 1. So anytime that I have a leading coefficient, that is a coefficient of x squared, that's something other than 1, my first step is to factor out that coefficient from this function. So if I pull out a 2 from each term, I'm going to have x squared plus 4x plus 3. And now the expression inside of the parentheses looks just like the quadratics that we worked with in parts A and B. So from here, I can apply the same procedure. I have 2 times inside the parentheses. I'm going to group my x squared and 4x together. I've got a plus 3 on the end. And now, in order to factor that quadratic as a perfect square, I have to think about what constant I want to add to x squared plus 4x. So here, my coefficient for x, which would be b, is 4. I'm going to take half of that value, which is 2, and then square it, which would be 4. And then on the end, I still have my constant plus 3. Now I've added 4, so I also have to subtract 4 within this set of brackets. And so now what I have is the following. I've got 2 times this quadratic in parentheses can be factored as x plus 2 quantity squared. And then my plus 3 minus 4 on the end leaves me with a negative 1. So distributing the constant 2, I have 2 times x plus 2 quantity squared minus 2 for my function h of x. So this would be that function in standard form, and from here we can find its vertex directly. Our vertex would be the point negative 2, negative 2. All right. So this example, we're illustrating a process known as completing the square, which is sometimes useful in writing a quadratic function in standard form, which can be useful if we're trying to find the zeros of a quadratic. So in general, we could use this technique that we just considered of completing the square to rewrite the general equation for a quadratic function, that is something of the form ax squared plus bx plus c, in the form a times x minus h quantity squared plus k, and get a formula for the coordinates of the vertex directly from the equation for the quadratic function in terms of a, b, and c. So if we do that, we get the following result, which is a formula for the vertex of a quadratic function, which is not written in standard form. So here, let's say we have the function ax squared plus bx plus c. So this represents a parabola whose vertex is hk, where h, that is the x-coordinate for our vertex, is negative b over 2 times a, and the k value, that is the y-coordinate for our vertex, is whatever the value of our function, f of x, is equal to when x is equal to h. So we take the x-coordinate for our vertex, and we plug it in to our function to get the corresponding y value for that vertex. All right. So as an example, in this next problem, we are asked to find the vertex of the parabola 4x squared minus 16x plus 9. And then we ask the question, is the vertex a maximum or a minimum for this function? So here, we're going to take as our vertex the x-coordinate, which we refer to as h, as negative b over 2 times a. So here, the value of b is negative 16. So our numerator, taking the negative of that value, gives us a positive 16. And then we divide by 2 times a, where a is equal to 4. So we have 16 over 8, or 2, for the x-coordinate of our vertex. So to get the y-coordinate for our vertex that we call k, we look at the value of the function f at the x-coordinate of the vertex, which we just found to be 2. So let's see what we have. Plugging in 2 for x, we have 4 times 2 squared, which is 4, minus 16 times 2, plus 9. So that gives us 16 minus 32 plus 9, which reduces to negative 7. So here the vertex of this parabola is the point hk, where h was 2 and k is negative 7. So we found our vertex, and we are asked the question, is this vertex a maximum or a minimum? Now, to determine that, we can think about which direction our parabola opens. In this example, we have a coefficient of x squared, which is 4. So here, our coefficient a is positive, which means that our parabola is opening upward. So in that case, our vertex is the lowest point on the graph of our function. So in our answer, we can say the vertex is the point 2, negative 7, which is a minimum. Okay. So let's look at some applications for these quadratic functions. So we've seen here that quadratic functions have graphs which are parabolas, and the vertex indicates the largest or smallest value on that parabola. That is the maximum or minimum value of some function. So these quadratic functions, or finding the vertex of a quadratic function, have nice applications in optimization. That is, say, maximizing profit, minimizing costs, maximizing output, things like this. So as an example of this, let's suppose that the daily profit from the sale of X units of some commodity is given by the following profit function, P of X, which is a quadratic here. And we see here that the coefficient of x squared is a negative 2, which means that this is a downward opening parabola. So the vertex of that parabola is going to give us the maximum profit. So in part A, we are asked to find the number of units that should be sold, so what is the value of x, so that this profit function is maximized. So here we're trying to find the vertex of this parabola. Now to find our vertex, well, the x-coordinate of the vertex, which we call h, is given by negative b over 2a. So here we have negative b, which was 40, divided by 2 times a, which was negative 2. So we have negative 40 over negative 4, or positive 10. So this is the number of units that we would want to sell. So we'll say the number of units to maximize profit is 10 units of whatever commodity is being sold here. We're not given what we're selling in the problem statement. And then in part B, we're asked, well, what is the maximum profit? So we know if we sell 10 units, the profit is maximized. To find the maximum profit, we would take 10, which yields the maximum profit, and substitute that value for x into our profit function. So let's see what we have. We have negative 2 times 10 squared would be 100, plus 40 times 10, plus 280. So this gives us negative 200 plus 400 plus 280, so altogether 480. So if we're measuring profit in dollars, we would have $480 profit for the sale of X units. All right. Now let's look at another example where quadratic functions might come into play, say in the relation between supply, demand, and price of some commodity. So in our previous section, we were assuming that the price and supply or price and demand were related by some linear function, but they may not always have a linear relationship. The relationship could be quadratic. So in this example, we are told that we have a supply function for some commodity, which is given by p equals q squared plus 20. Or here, since this is a supply function, we might write this as s of q is equal to q squared plus 200. And we have a demand function that is given by p is negative 10q plus 3200, or d of q is negative 10q plus 3200. So here our supply function is quadratic and our demand function is linear. So in part A of this example, we're asked to sketch the graph of the supply and the demand function on the same axes. So let's see if we can sketch the graph of these two functions, at least get a rough sketch. So here we're plotting price as a function of the quantity supplied or demanded. So let's start with our supply function, which I'll plot in red. So it is a quadratic function, q squared plus 200. So the vertex of that parabola would be the point 0, 200. So when q is 0, the price p would be 200, and then we had a coefficient of q squared of 1. We had 1 q squared, so this is an upward opening parabola. Looks something like this. So this would be our supply curve. Now our demand function was linear. Its graph is going to be a straight line, and we see that when Q is equal to 0, the value of D, the demand, would be 3,200. So our y-intercept here is 3,200, and the slope of our line is negative 10. It was 3,200 minus 10Q. So we have a line which is decreasing as Q increases, and when the value of Q is equal to 320, our demand is equal to 0. Now, how did we find that value? Well, we could set the demand function, which was negative 10Q plus 320 equal to 0. We find that 10Q has to equal 320. So Q is, or 3,200, excuse me. So Q is then our 320. So here we've got a rough sketch of our supply and demand curves, and we can see from our sketch here that these two curves will intersect in some point. So this point of intersection of the supply and demand curves are what we call the equilibrium point. So in part B, we're asked to find that equilibrium point. What is the price and the supply, or the quantity supplied or demanded in equilibrium? So in order to find this equilibrium point, we're going to set supply equal to demand. So that is, we're going to take Q squared plus 200 and set it equal to our demand function, which was negative 10Q plus 3,200. So to solve this, we can move everything to one side of our equation, say the left-hand side, and I would have Q squared plus 10Q, and then if I subtract 3,200 from both sides, I would have minus 3,000 is 0. So from here, there's a few ways we could go about solving for Q. I could write this in standard form for the equation of a quadratic and then solve from there. Or I can try factoring this. And here we see that this quadratic can be factored as Q plus 60 times Q minus 50 is equal to 0. So it follows that Q could either equal negative 60 or positive 50. And in this problem, since here Q represents a quantity supplied or demanded, we know that we can't have a negative value for Q. So this negative 60 value we would reject. It doesn't make sense when we're thinking about the physical interpretation of the problem. So here, the value of Q that we're interested in is 50, and we need to find the corresponding price for that quantity. So here to the side, if Q is equal to 50, then the price, P, is given by negative 10 times Q, which was 50, plus 3,200. So here I'm making use of my demand function. I could also plug 50 into the supply function, and I'll get the same output since Q equals 50 is the value that made those functions equal. So here we have a negative 500 plus our 3,200 leaves us with 2,700. So the equilibrium point would be the point given by 50 and 2,700. And then in part C, we're asked what is the equilibrium quantity and the equilibrium price. Well, those are just the coordinates of our equilibrium point. So here the quantity is equal to, we found 50 for our value of Q in equilibrium. Remember, Q represents quantity. And the equilibrium price would be the corresponding value for P, which we found to be 2,700. All right. Now in this next example, we have a similar problem to the last one, where we have a revenue function R of x and a cost function C of x for some particular product. And they are given by R of x and C of x, these revenue and cost functions. And we're told that these functions are valid only on the domain of values where x is between 0 and 150. Outside of that range of values, maybe one of these functions is negative. We can't have, say, a negative cost, for instance. So we're asked here to find the number of units that would be produced in order to break even. So if we know what our cost and our revenue is, depending on how many units which are being produced, we want our break-even point. Now recall that the break-even point is the point where we let revenue equal to cost. So here we're going to let our cost function equal revenue. So let's look at our cost function. We had the function 65x plus 7,000. We're setting that equal to our revenue, which is 300x minus x squared. And we now want to solve for x. So here, let's move everything to one side of our equation. So if we move everything to the left-hand side, if I add x squared to both sides, I would have 1x squared. Subtracting 300x from both sides, I would have 235x. And then I've got my constant plus 7,000 is equal to 0. So now, if we want to solve for x, well, there's a few ways we could do it. One way would be to try to factor this expression. And here we can see that this could be factored as x minus 35 times x minus 200 is equal to 0, in which case x could be equal to 35 or 200. So we have two values of x here for which revenue is equal to cost. But recall in the problem statement that this cost and revenue function was only valid on the interval from 0 to 150. So this value of x equals 200 we have to throw out since it does not lie in the domain of those functions. So we're left with a value of x equals to 35. So here this would be the number of units that we need to produce in order for cost to equal to revenue. All right. Now another way that we could go about solving for this x in this quadratic would be by completing the square. We could rewrite it in the standard form for the equation of a quadratic. So to illustrate how we would do that, we would have our x squared minus 235x, which I would group, plus 7,000 is equal to 0. And then by completing the square, I would take x squared minus 235x, and the constant that I want to add on the end would be half of this b coefficient squared. Now half of 235 isn't a nice integer value, but I could write it as 235 divided by 2, and I would square that value. And that's the constant I would want to add on the end. Now I still have my plus 7,000, and I would then have to subtract the same constant that I added, 235 over 2 squared, and that would be equal to 0. So from here, we could rewrite this as x minus 235 over 2 quantity squared. That would then be equal to 235 over 2 squared minus 7,000. And then to solve for x, we would have to take the square root of both sides. So I would have x minus 235 over 2 is equal to plus or minus the square root of this quantity. And then I would add my 235 over 2 to both sides. All right. So from here, after simplifying, we find that we would have the same x values that we had found above, namely 35 and 200, after some simplification here. So again, we end up with the value of 35 if we use that same approach, but we can see in this case that the numbers get a little messy. All right. So in this example, we are told that the manager of a bicycle shop has found that a price in dollars of P of X is 150 minus X over 4 per bicycle. Or at that price, he can sell X bicycles. So here in part A, we are asked to find an expression for the total revenue from the sale of those X bicycles. So let's think about how to find revenue. So our revenue function, let's say R of X, is found by taking the price at which you are selling a commodity per unit, and then you multiply by the number of units that you sell. So it's how much you're charging for one unit multiplied by how many units that you've sold. That gives you your revenue, or how much money you're bringing in. So in this example, our revenue function, R of X, would be given by the price per unit, which in the problem statement we were told is 150 minus X over 4 dollars per bicycle. And then we're multiplying by the number of bicycles sold, which was X. So distributing our X, we have R of X is 150X minus X squared over 4. So here our revenue function we see is quadratic. So in this example, part B, we're asked to find the number of bicycle sales that leads to a maximum revenue. So looking at our quadratic here, the coefficient of x squared would be negative 1/4. So this is a downward opening parabola, which means that the vertex would correspond to a maximum. So we want to maximize our revenue, and we need to know how many bicycles are needed. We need to sell in order to do that. So to find the vertex of a parabola, or the x-coordinate of the vertex, we take h, as negative b over 2 times a. So here we have negative b, which was 150, divided by 2 times a. Now we've already said that a was negative 1/4. So we have a negative 150 divided by 2 times negative 1/4 is negative 1/2. So dividing by negative 1/2 is the same as multiplying our numerator by negative 2. So our negative 150 times negative 2 would give us a positive 300. So we want to sell 300 bicycles in order to achieve the maximum revenue. And then in part C, we ask the question, well, what is the maximum revenue? So in the event that we are selling 300 bicycles, our revenue is maximized, and the value of our revenue would be R of 300. So plugging that into the revenue function we found in part A, we have 150 times 300 minus x, which was 300 squared, over 4. So this gives us 45,000 minus 90,000 over 4, which is 22,500. So we are left with 22,500 as the maximum possible revenue here. All right. So let's take a look at our last one. In this section, we have the manager of a peach orchard is trying to decide when to arrange for picking their peaches. So we know if they are picked now, the average yield per tree is 100 pounds, which can be sold for 40 cents or $0.4 per pound. And past experience shows that the yield per tree will increase by 5 pounds per week. However, the price will decrease by about 2 cents per pound per week. So if this manager of the peach orchard waits to harvest the peaches, they can harvest more. However, the longer they wait, the price will drop. So the goal here is to determine, well, when exactly should they harvest these peaches in order to maximize their profit or maximize their revenue. So we'll break this problem up into some parts. In part A, we're told to let X represent the number of weeks that the manager would wait from now. And then asked to find the price per pound. So here, our price per pound is currently, so if they pick these peaches now, they can be sold for 40 cents per pound. So we would have a current price of $0.4 or 40 cents per pound. And for each week that the manager waits, we are told the price will decrease by 2 cents per pound per week. So from our starting value of 40 cents a pound, we will have a decrease by 2 cents or $0.02 a week, and then we multiply by X, which is the number of weeks that we decide to wait. So our price per pound would be this 0.4 minus 0.02X. Now in part B, we ask the question, well, find the number of pounds per tree. So what will our yield be for each of these trees? So here the yield in pounds per each tree would be found by taking the current yield. If we were to pick them right now, then the average yield per tree is 100 pounds. So if we were to pick them right now, we would start with 100 pounds on average per tree. However, if we decide to wait, then the yield per tree is increasing by 5 pounds per week. So if we decide to wait from that average of 100, we would increase 5 pounds per week times x, the number of weeks that we decide to wait. So given this information in part C, we're asked to find the total revenue produced from a single tree. So here our revenue, which we'll call R of x, would be found by taking the price per pound, so how much we can make for each pound, and then we would multiply by the number of pounds per each tree. And that would give us the price per tree, or our expected revenue per tree. So let's look at this. We have revenue, which we'll call R of x, is the price per pound, which we found to be 0.4 minus 0.02x, and we're multiplying by the pounds per tree, which is 100 plus 5x. So let's see what we're left with. If we expand this, we would have 0.4 times 100, or 40, plus 0.4 times 5x, so that would be 2x, then minus our 0.02x times 100 would be minus 2x, so that cancels with our plus 2x. And then our last term, we would have 0.02 times 5, which is 0.1 x squared. So we have the following function for revenue. So then in part D, the question is asked, well, when should these peaches be picked in order to produce the maximum revenue? So we want to maximize this quadratic function R of x, which we can see has a negative x squared coefficient, so it's opening downward, and that vertex does correspond to a maximum. So in order to maximize our revenue, we need to find the value of x for our vertex, which is given by h equals negative b over 2a. Now in this example, our revenue function only involves a constant in x squared. There was no x term. So our value for b is 0. And then we're dividing by 2 times a, which was negative 0.1, but 0 divided by any non-zero number leaves us with 0. So what does this mean in relation to the problem? Well, recall that x was the number of weeks that the manager waits, so they should not wait. They should be picked now. All right. And then in part E, we are asked what is the maximum revenue. So if they are picked now, that is if x is 0, they wait 0 weeks. The revenue is maximized, and plugging in 0 for x in our revenue function, we would have a value of $40 we were measuring in per tree. All right. So in this last example, we're illustrating some applications of quadratic functions in making some sort of business decision where we've got multiple quantities varying over time. We'll see other examples similar to this, but a little more complex later in the course when we get into our Chapter 12 material.